you warmly welcome at this joint seminar of Marka's Complex System Research Center and the Field Theory Department. And we are happy today to welcome Professor Jerzy Kowalski-Glikman, Professor of both Wrocławski University and also National Center for Nuclear Research in Warsaw. And the Professor Kowalski-Glikman is well known because of his contributions to quantum gravity, especially to his co-founder of doubly special relativity, triple special relativity, and relative locality concepts, which are, very well, I would say, theoretically established concepts in quantum gravity. So let us start.
Okay, thank you. Well, actually, I'm not going to talk about neither of those, but let me tell you about something that I also contributed to. That was the research program that was actively developed in about 10 years ago. So I'm a little bit worrying about presenting it, because usually when you actually return to something that you've been doing some time ago, it's usually considered to be a sign that you're getting old and you don't have new ideas, so you need to actually use your own ideas of the past. But as a matter of fact, I was kind of thinking about this for a long time, and the reason I'm actually starting thinking about it more is that now I see that there are some perspectives or possibilities of solving the problem that remained unsolved for the last 10 years. I will tell you a little bit about it, but basically what I wanted to tell you is to just to give you some overview of the topic. And if I have time at the end, I will tell you a little bit about this new research programs or the new research project that will possibly start in the near future. So let me start. Okay, this talk will consist of 4 parts. I will start with motivation as usual. Then I will tell you about gravity as a constraint BF theory. So this will explain the title. Then I will tell you a little bit about coupling particles to gravitational field in this formulas, which is pretty interesting by itself. And then in the end, I will briefly describe the developments that took place in the last, in about 10 or 8 years ago, and then it will be a good starting point then to tell you a little bit about these new developments that I think might be pretty interesting. Okay, so what are the motivations? Actually, I will return to this motivation because at this moment, after 10 years, this motivation do not really look that appealing as they were at the very beginning of this research of this program, which was, I don't know, in around the year 2005. On the other hand, the program by itself proved itself pretty interesting, so these motivations are not really needed. But let me actually, I think there are some observations that are nevertheless pretty interesting and worth thinking about. Basically the problem is how to make gravity quantizable. And we know, of course, that there are some problems. There are problems in perturbative quantization of gravity. So let us try to trace the reasons why it is so, and to start, the first thing that comes to mind is actually to compare 4-dimensional gravity with a theory which is simpler, but in principle should be as difficult to quantize, which is three-dimensional gravity, which is described by topological field theory, with the action being, this is the standard Einstein action for 3-dimensional gravity. This is a 3-dimensional This is the three-dimensional frame field. This is the three-dimensional Lorentz connection, and the action is this. You can check that's written in forms, but you can check that it actually reproduces the standard action of gravity in 3 dimensions, or as was actually observed first by Townsend and what was his name? You remember? Aljagar, yeah. And Witten. Actually, the action can be the action for gravity can be derived from this Chern-Simons action. So Einstein gravity can be derived from this Chern-Simons action for the Poincaré group. That can be generalized to the case of positive or negative cosmological constant just by changing the gauge group. But the real observation is, which proved to be extremely important for both physics and mathematics, that gravity in 3 dimensions is described by Chern-Simons theory for particular gauge group. Okay, so Witten.
So one is just usual Lorentz connection, the other is Poincaré. You said the other one A capital A.
Sorry.
Omega, small omega.
Omega is a Lorentz connection, is a frame field in 3 dimensions. A is a Poincaré connection, which essentially contains both. But I will explain it in 4-dimensional case. I will explain it in details. So the structure of A in terms of E and omega is the same in 3 and 4, and it will become clear in a moment.
So the translations we can see.
All right. Okay, so, well, for those who know, this is pretty, well, this was pretty beautiful piece of theoretical physics. Witten used this insight into quantizing. So he proved that this 2+1 dimensional gravity can be quantized non-perturbatively, and there were many of papers which actually approach this quantization. One can couple to matter, 3D gravity to matter, treating later as a topological defects. It's a kind of a natural geometrical coupling of gravity to matter, at least in this framework, which treats matter as topological defects, and I will return to this when I will discuss the particles in 4D. What is actually pretty interesting here is that when one integrates out gravitational degrees of freedom, so suppose I have a system which consists of 3D gravity and some particles, then if I integrate out the gravitational degrees of freedom, which is possible because the theory is topological, so there is a finite number of these degrees of freedom, you can integrate them at least formally, or more or less, or less formally, so there's good arguments how you can do it. So one way or another, if you solve for gravitational degrees of freedom, either in path integral formalism or using some combinatorial quantization method, at the end of the day you obtain, since gravity is already taken care of, one obtains an effective quantum field theory of matter degrees of freedom. It turns out that this theory is quantum deformed, so it's described by quantum deformed system with a Hopf algebra of spacetime symmetries. This is what we know about 3D gravity. And well, what's remarkable about this action, and this is one of the observations I wanted to tell you, although I am not sure how seriously it should be taken, the major difference between this action, which is the action of gravity in 3 dimensions, and this action, which is the action of gravity in 4 dimensions, this is a cosmological term, and lambda is not present here explicitly, but you can think of this as a Burr form of the Einstein action. You see that the major difference is that this kinetic term here is 2 linear, right? Because this curvature of omega contains the term df, so there is the leading coordinate term here is edf. Similarly here is ada, so this leading kinetic term is quadratic. However, in an Einstein action, this leading kinetic term is actually trilinear, which immediately makes it kind of hard to imagine I mean, if you have a quadratic kinetic term, then you know this standard quantum field theory, perturbative quantum field theory of expansion around, you know, the expansion in the Fock basis and treating fields as a bunch of oscillators with a natural Fock vacuum. It works. However, here you have a different kind of a vacuum, which would be described by something. So you have this kinetic term is trilinear, and all this intuition that we have about the standard perturbative quantum field theory doesn't seem to work, at least naively doesn't seem to work here. And well, you may claim that the problem of quantization of four-dimensional gravity is actually partially related to this fact, or at least there was one of the motivation for this formula that I am going to tell you in a moment. So the one thing you want to actually, one problem you want to solve is to actually this trilinearity problem, which is a basic problem, as it seems, in quantum, leading to the problems in quantum version of gravity in 4 dimensions. Another problem is that, and this is something to be said, that people claim to be the major problem with perturbative quantization of gravity. So if you think about the metric formulation, what you naively do, I mean, what you do in starting the perturbative quantum gravity, what you do, you decompose the metric, so the field describing gravity, into background part and some perturbation about the background, which is fine in the case of in the standard quantum field theory, because you have a gauge invariant, so to say, gauge invariant vacuum, so you can actually expand around the vacuum without really breaking the symmetries. However, here in gravity, this immediately manifestly breaks the standard, the most basic diffeomorphism invariance or general covariance of gravity. And that's what people think, or at least, well, if you look at the textbook, standard textbook on quantum gravity, that's what all the authors actually say is the basic major reason why it's so hard and difficult to quantize gravity. Essentially, the reason is that you break the symmetry, and the theory doesn't like it. So all the problem with non-normalizability and stuff are actually related to this. Can be taught to boil down to this breaking of symmetries of gravity of the theory that is necessary in order to start perturbative, quantum perturbative theory. The problem is that both these arguments seemed pretty solid at the time when this BF formulation was first introduced, and that was a strong argument in favor of it, because it somehow actually overcame both these problems. However, the point is that in the meantime we learned that most likely there is a perturbative gravity. I mean, the n equals 8 perturbative supergravity most likely exists, and it's a finite quantum field theory. And of course it suffers from both these problems. So these arguments do not seem to be that strong as what people thought, I don't know, 15 years ago. Still, perhaps we can actually try to formulate gravity in such a way that these problems are not present, at least manifestly or explicitly. And this is the major motivation for this formulation that I'm going to tell you about. So let me start with the description what this formulation is. I would like to construct gravity in 4 dimensions in such a way that it's as similar to 3-dimensional case that we control and we love, because it's a beautiful theory from many points of view. And since in 4-dimensional gravity is certainly not a topological field theory, meaning that it has local degrees of freedom. We know about this local degrees of freedom because we feel gravitational attraction. And certainly that proves that there are local degrees of freedom of gravity, because, you know, gravity really attracts. So the question is, can we actually present the gravity in the form in which it has a topological part plus something that we consider to be, that we can regard as a small perturbation? And this is the construction about it. This small perturbation actually, it's a little bit tricky, because you really need to understand what small means, and I will discuss it a little in a moment. But let me actually turn just to the construction of the theory. So the first point of the construction is to start with the symmetry algebra in the case in which the cosmological constant is present. Well, we know that, you know, in special relativity, that the symmetry of flat space is the Poincaré algebra. So you can generalize it to gravity and say, well, the gravity is something like a theory of local Poincaré symmetry. However, it turns out that as a starting point, you really need to start with a theory with local either de Sitter symmetry or anti-de Sitter symmetry, which is the symmetry of the de Sitter space, positive curvature, four-dimensional space, or the anti-de Sitter space. And we know that in the limit in which cosmological constant goes to zero by enormous Wigner contraction, you can actually from both this algebra in the contraction limit you can get Poincaré. So we need to start with a theory with cosmological constant, and it will become clear in a moment why it is so. So I have this algebra. This Lie algebra of both groups has this structure. These are orthogonal groups, so the structure of the commutational relation are canonically of this form. Then you can decompose, and this decomposition will be essential. You can decompose each of this group, and also Poincaré group actually, into the Lorentz sector with generators MAB. These are the Lorentz generators. There are 6 of them. And the 4 translation generators. And if you actually substitute this decomposition here, you will find that the following structure. The Lorentz algebra has its natural SO31 structure. The Lorentz symmetry, which is rotational boost acting on momentum, actually reproduces momentum. And the only difference, and in Poincaré case, 2 momenta will commute, but in the case in which cosmological constant is non-zero, 2 momenta actually commute to Lorentz transformation. This is the standard structure of the de Sitter or anti-de Sitter group. Here you have a cosmological constant basically when you actually switch to physical dimensions. All right.
And you don't consider time translation as well?
Yeah, sure. Yeah, this is the 3-dimensional. Sorry.
There was special translation. Generators of special translations. PB, right? PA?
A goes from 0 to 3.
From 0, okay, including 0. Okay.
So this is, everything is space-time. Okay, so let's start as a starting point. Let us consider the following theory. This is the theory which is called the BF theory. It's called BF theory because it contains a field B, which is a 2-form valued in the algebra of SO41, but it can be SO31, SO32. So it's either de Sitter or anti-de Sitter algebra valued 2-form. This is the connection A, which is again the connection valued in this algebra. This is the curvature of this connection, which is again by construction a 2-form. Okay, so you can construct this term. This term, and that's why this theory is called BF, right? This theory is topological because when I take a variation over B, the equation of the field equation for B is that F is equal to 0, which means that the curvature of this connection is 0. So it's essentially, this theory describes just flat connections. There is another term which in the context of BF theory is called cosmological term, but watch out, this doesn't, as you will see in a moment, this doesn't have to do with cosmological constant, but in gravitational context that I will describe, it has to do with inertia parameter. But clearly, if in 4 dimensions, this term actually construct in any dimension. As you see, this is a 2 form, and this can be in 2 dimensions, this will be 0 form, in 3 dimensions, this will be 1 form, in 4 dimensions, it will be 2 form, in 5 dimensions, it's going to be 3 form, and so on. So this term can be constructed in any dimension. However, this term actually can be constructed only in 4. Right, because B is a 2 form there, and this makes it into the 4 form, which is the right way. Now, this is the theory which is topological, and also it has actually a gauge group which is a little bit too large, because the symmetries of this theory contain SO4-1 symmetry, which is kind of a analogy, which is a group which is analogous to Poincaré group in the case of cosmological constant, but it also contains, it's manifestly diffeomorphism invariant, right? So it has too many symmetries. It's not gravity, and certainly it's not gravity because it does not contain local degrees of freedom. So how to make it into gravity? Well, it turns out, which is, I think, pretty beautiful. It turns out that it's sufficient to add the following term. Let me pick that one direction 4. Okay? Then I can construct a term like this. Okay? Which means that this, because of this epsilon symbol, this indices I, J, K, L can only take value can only be equal from 0 to 3, which makes this symbol essentially the invariant symbol of Lorentz group. And this term, you can check it explicitly, is manifestly breaking this algebra, this symmetry, but it breaks it exactly down to the Lorentz symmetry. This is exactly what we want. Right? Because gravity is thought to be a diffeomorphism invariant theory with local Lorentz symmetry. In fact, you can check that there is kind of a transition, one-to-one, on the shell at least, a one-to-one relation between diffeomorphism and local Poincaré symmetry. So you can start with the local Poincaré symmetry, in principle the theory of local Poincaré symmetry, but then it turns out that the local Poincaré symmetry must be related to diffeomorphism. So this is the theory which it first contains the topological part. It contains a gauge breaking part which breaks the symmetry down to what we want, to the local Lorentz symmetry. This parameter alpha, if you consider this parameter, this part, as a perturbation of this part, then we indeed have what we wanted, namely the topological theory plus some perturbation. The problem is, is it really a small perturbation? And I think it is not, and this is one of the open problems, that nobody really could make it into the theory in which this is the topological part, but this is in a kind of a precise sense can be really said to be small. But before going to this, or after making this comment that the perturbation theory in this part is pretty hard, and nobody was, and people were trying. I mean, I was trying with some people and students, and we never succeeded in finding something really interesting from it. But after making this comment, I would like to convince you, this looks pretty strange, but I would like to convince you that this theory is actually both classically and quantum mechanically exactly equivalent to general relativity, up to the topological terms. Well, so what do we do? Well, first of all, you really need to, in order to find what is the relation between this theory and gravity, you really need to find out how this theory, in which way this theory describes the gravitational degrees of freedom. Well, there are two basic fields of gravity, which is the frame field, which is Vierbein in 4 dimensions, and the Lorentz connection field. Now, the field A, the connection A, has, okay, I can naturally decompose the indices here into the index AB, which are the index, this pair of index describes the Lorentz subgroup. So this is the Lorentz part of the connection. And there is the part of the connection which has the one index A. Here the index is fixed to be 4. And I would like to identify it with a frame field. The problem is, however, and this is why we really needed that, as it turns out, we really needed to start with a situation with cosmological constant. The problem is, however, that canonically the frame field is dimensionless and connection has canonical dimension of inverse length. So there is kind of a length parameter that I really need to introduce here in order just to make the dimension right. Okay, so in order to identify the frame field with some part of connection, I really need to do a length scale to do that. Okay, and then there is a relation, as well, you can check out that. Then what you do? Notice that this theory is quadratic in field B. There are no derivatives of field B. It's only algebraic the dependence. And then, since this is algebraic dependence, which is at most quadratic, I can actually solve the equation of motion for B, field equation for B, and substitute the result back to the action, obtaining the theory with exactly the same physical content. Or equivalently, in the quantum mechanical language, I can actually plug it into the path integral and integrate out the B field, explicitly obtaining some effective theory for for A. And then, as a result, you get the following theory. The effective action expressed in terms of omega and E, so Lorentz connection and the frame field, contains this part of the action that I will discuss in a moment, and it also contains 3 topological invariants. This is the Poincaré, the Pontryagin index. This is the Euler class, and this is something which is called the Niang class, which has this complicated form. So we have some topological invariants. There, if you have a if you have a theory on the boundary, on the manifold without boundary, they are completely irrelevant, because only the bulk degrees of freedom which are described by this part of the action are relevant. In the case of boundaries, actually they provide extremely interesting and important and not completely understood information.
What is the meaning of this last class? Yeah.
Oh, this is something. This is a topology. Well, I'm not sure what is. It's related to torsion. So this is the invariance which is non-vanishing only in the presence of torsion. And from this reason, I'm not sure. I don't really know its geometrical meaning. Perhaps you guys do.
Torsion.
There's something of torsion. I mean, some invariant, it involves both curvature and torsion. Usually, when torsion is 0, this invariant actually vanishes identically. Okay. So what is the first term? The first term is actually, as expected, just the Einstein action. Well, a little bit modified. So it's not really this is the Einstein action modified by the Hall's term. So let me discuss it in all the terms here. This is the standard Einstein action. You can written in the form language. So either you know it or you believe it. If you want, you can always do the calculation and you got it. That's actually a pretty nice calculation in differential geometry to show that this is nothing but the square root of g times r of g, or r of gamma, because it's first order formulas. This is a cosmological constant term, which is easy to understand because this guy here is just a volume element, right? So this is just a cosmological constant term. This term, however, is actually pretty funny. This is something which is called, Hall's term. This term is not topological because its variation is not zero, and so its variation is non-trivial, contains non-trivial bulk terms. But funny enough, actually, when torsion is zero, this term vanishes identically, and the equation contribution to field equation actually vanishes identically. So this term, so from the point of view of the field equation, this term is completely irrelevant. However, it is actually crucial when one considers the symplectic structure of gravity, and this is the parameter which is called Imirci parameter, and the symplectic structure here turns out to be dependent, of course, of this parameter, and this is the reason why Imirci parameter appears, for example, in the loop quantum gravity. So as a starter for loop quantum gravity, so in order to get the right symplectic structure of which is the starting point for the construction of loop quantum gravity, you really need to add this term. And as a matter of fact, this term was actually discovered by Holst just because Holst wanted to find a classical variational principle that would lead to the symplectic structure which is needed for quantum gravity. So this term is irrelevant for field equation, at least where fermions are not there. It's, however, crucial to obtain loop quantum gravity, so to say, symplectic structure on the phi space. You may ask yourself a question: does when this term is actually going to be relevant? For example, you may ask yourself: is this term becoming relevant in supergravity? And turns out it's not. So the supersymmetric, when you do supergravity, you really need to add some kinds of supersymmetric extension of this term, and then the total contribution of this both terms, so this term and its supersymmetric extension, is again zero. So supergravity actually prevents gamma to become parameter relevant for the from the field equation. However, if you actually couple gravity to arbitrary fermions, not supersymmetric, of course, this term will become relevant because the fermions will be would be the source for torsion. Okay. So let me just summarize. What can we do? I have about 25 minutes left. Okay, good. So I already mentioned that the problem is that, again, the initial motivation was when people got this action, that was Smolin, Starodubtsev, and Friedel, they were extremely happy because initially they thought that this term can be really regarded as a perturbation. So you can start with the theory with alpha equals 0 and then do the perturbation in non-zero alpha. The problem is that you cannot do that, and the reason is pretty simple. So at least nobody was able, well, perhaps I said it too strongly, nobody was able yet to do this perturbation theory, and the reason is that the theory for alpha equals 0 and alpha not equals 0 are different theories. Right? For alpha is equals 0, the theory is topological. There are no local degrees of freedom. For alpha equal non-zero, whatever the number it is, it contains different degrees of freedom, which makes it kind of very difficult to think about this topology, the well-behaving or well physically defined perturbation theory with this parameter alpha. And so there was some kind of the same problem actually appears similar problem, analogous problem appears in the BF formulation of Yang-Mills, because you can think of Yang-Mills theory of construction of Yang-Mills theory in the kind of a similar form. And there were some Italian people, Cataneo, some people from Florence, I think. There was a group of people who actually investigated this theory in details. just trying to understand, is it possible to make this expansion as alternative expansion to the perturbative expansion? And the end result of their investigation was that it's impossible. However, the problem is open here, and I think it's a pretty interesting problem, and this is one of the reasons I really wanted to start again investigating this type of theory, just to try to understand better if indeed it's possible somehow to establish a perturbation theory in this small parameter. Well, one of the reasons is that if alpha goes to 0, then the theory becomes topological, and then when I couple it to particles, I hope to have to obtain a situation which is similar to that of 3D gravity, which makes the dynamics kind of deformed, and quantum groups start playing a role in this whole effective theory, which then would lead to some rich and interesting quantum gravity phenomenology. So the basic idea was really to establish or to derive these deformed symmetries like Kappa-Poincare from fundamental formulation of gravity, but unfortunately we haven't been able to do that. So let me now briefly tell you a little bit about the coupling to particles. I will not go to all the technical details. Let me just roughly tell you what is the idea. It's technically a little bit complicated, but the idea is, the basic idea is actually simple. Okay? Well, this is how it is written in the paper, but let me explain what does it mean. So suppose I have a particle. Okay, I have a particle in gravitational field, and I know that my gravitational field is actually described by this connection. Okay, this is a connection which has value in the Sitter algebra. Okay, good. So how can I characterize the particle? Well, in order to make this action, in order to make it into action, so starting from connection, and in order to construct the action, I really need to trace over gauge degrees of freedom, right? If there was a single A here, when I take the trace, I would just get 0, right? Because, you know, the matrices are traceless. So I need to pair it with some element of the algebra. Let me call it K. Okay, I have some element of the algebra. And then this object is a kind of well-defined action. Well, this action, actually, if you think about it a moment, certainly breaks all the symmetries of the theory. Well, it breaks the diffeomorphism symmetry because you associate it with some particular word line, and it breaks gauge symmetry because there is just a fixed element of the gauge algebra, right? So forget about the diffeomorphisms are not that relevant, but what is relevant is the gauge symmetry is actually broken here. Oh, because this element is just a particular element of the gauge algebra. But this is exactly what we want.
Does this procedure works for any gauge field? Or just
Yeah, well, it's gauge you just for young males too. Yeah, sure. Well, it goes for coupling to, it works for coupling, I mean, but the interpretation that I'm talking about now is just space-time and gravitational. Think about this symmetry. Forget about the cosmological constant for a second, just to make it clear. And think, what are the local gauge symmetries? Well, the local gauge symmetries are the Lorentz symmetries, right? There are Lorentz symmetries in that translations, basically, okay? Okay, so suppose somehow that this guy describes a particle at rest. Then we know, so suppose that this action describes a particle at rest, and let me make a gauge symmetry, a gauge transformation. When I make the gauge transformation, this guy will not become invariant. Actually, it will explicitly depend on the gauge parameter. But what is the gauge parameter? Well, the gauge parameter is a Lorentz symmetry, and translation. So perhaps this gauge parameter actually describes the dynamics of the particle. It just tells you what is the momentum of the particle by boost. Boost tells you what is the momentum of the particle which has some given mass. Well, it also tells you what is, if you have a spinning particle, the Lorentz transformation is essentially telling you what is the actual angular momentum of the particle given its spin at rest. The translation is actually telling you where the particle is. Okay? So in fact, the dynamics of the particles can be associated with the Poincaré transformation, right? For any particle, the Poincaré transformation is essentially telling you how to obtain the actual kinematical state of particle in terms of its rest property, in the rest frame. Does it work? Well, you need to check. Well, first of all, I then take a particular value of k. Well, k will describe a mass, the rest mass of the particle, with the to which I associate the particular generator of the gauge algebra, which is P0, which is natural, and the spin of the particle, some parameter s, which describes its angular momentum at its rest frame, associated with the rotation generator M23. Well, you may ask, does this procedure works for the massless particles? And my answer would be yes, I think it does, though I never had a graduate student who I could give this exercise. So if you actually can generalize this to the massless case and work it out completely, I think it would be a nice paper. If anybody is interested in this project, I invite him or her to actually get in touch. So, and this is essentially what I told you. Actually, here we do a little bit, it's slightly different because the gauge transform, because of the fact that my theory that I have here is not a Poincaré, local Poincaré invariant, but it's Lorentz invariant only, right? Because I couple it to this theory that the gravity part that I described before, I just consider gauge transformation, which described by Lorentz group. So the gauge transformation will tell me what is the boost that actually makes the particle moving, and there is a translational part which is associated with the coordinate transformation, which essentially tells me where the word line of the particle is, right? The diffeomorphism actually moves the word line on the manifold, and the gauge group, so the diffeomorphism tells me where the particle is, and Lorentz transformation tells me how the particle moves. Okay, good. So now what I do, I take, for the Lagrangian, I take instead of the Ka, I have the K times gauge transformed A, and, well, so let me skip this thing. I get some action, which is expressed in terms of the variables are H, which is the Lorentz transformation, the Lorentz group element, and the position of the particle, which is Z of tau, which are the free variables that I can vary about, and using this I actually get two equations. One of these equations is this is the spin precession equation, which takes this form, which is kind of a general, curved space-time generalization of the condition that angular momentum is preserved. And the second equation, which is the generalization of the geodesic equation, is something which is called the generalized Matheson-Papa-Petro equation, which is the equation which tells you how the particle moves when it has a spin described by S. So you see there is this nice spin curvature coupling here. This part is essentially the standard geodesic part. This is the spin curvature coupling, and there is also in the presence of torsion, and this is a kind of a new result we got just by accident. I think nobody ever thought about this term before. This is how the Matheson-Papa-Tetrov equation looks like in the case in which a torsion is present. This is exactly the equation that we want to obtain, which means that the formalism a posteriori, this indicates that this formalism actually works and leads you to the right equation. However, the technical details there are slightly complicated. Also, as a kind of a consistency check, you can actually look how the field equation look like in the presence of particles. Then you have a torsion equation. Torsion is actually, the source of the torsion is a spin. It should be, well, I have this P here, the index P denotes that the spin is actually, here it should be some kind of a delta function which puts the spin just on the word line of the particle. And the curvature part, this is the Einstein tensor, this is the Holz term, which is present here because the torsion is non-trivial, right? The torsion is non-zero, so this term is present. And this Einstein part is essentially, source for the Einstein part is essentially the energy momentum density, or the energy momentum concentrate on the word line of the particle. This is the structure of the theory. I perhaps skip this one, which is actually a pretty interesting thing, and I will tell you if you're interested. I will comment on this at the very end. So let me actually tell you about the other developments in this. One of the things I would like to do is actually to do the Hamiltonian analysis, hoping, so the hope was that when you do the Hamiltonian analysis, because of simplicity and this decomposition into, into the topological part and kind of dynamical part, this perturbation, this small part, which hopefully small part that describes the perturbation about the topological theory, somehow the Hamiltonian analysis will reflect this, and indeed it does. However, it doesn't really simplify anything, so it doesn't clarify anything, and that doesn't lead to any simplification of the theory. Well, the Hamiltonian analysis gives you the following result. In the case in which alpha equals 0, alpha is this parameter that governs this, this non-topological, this local term. For alpha equals 0, the theory is topological, which in this language actually translates into the simple conclusion that there are only first-class constraints, and the number of first-class constraints is exactly equal to the number of local degrees of components of the field. Which essentially is telling you that, well, there are no free degrees of freedom, local degrees of freedom in the theory, right? I mean, all the degrees of freedom are solved already by, are constrained by the first-class constraints. And then, when you actually switch on alpha, some of the first-class constraints become second-class constraints, which essentially is telling you that now the system is less constrained than it was, and there are some degrees of freedom that are not constraints, which is exactly what you expect. But then, for alpha not equal 0, you essentially, what's happening is that essentially at the end of the day, after a few technical steps, you land at the same theory, at the same Hamiltonian structure as the one of the standard gravity in Holst formulation. So nothing is simplified. And then the only way to really analyze this system, which is something that you should remember, that the only way to analyze this system is actually, because it's so complicated, the only way that people know how to deal with it is to partially fix the gauge, and that's how you end up with the the standard phase space of loop quantum gravity. It's not that there is something necessary about this phase space of loop quantum gravity. That's the only way that actually people were able to find that worked and lead to the system that is tractable. Okay, so this is about Hamiltonian analysis. There is something pretty remarkable here in the case of boundary and differentiability. you know that if you have a theory with a boundary, you must be pretty careful about the boundary term. So if you have a Lagrangian on the manifold, so variational principle on the manifold with boundaries, you really need to be pretty careful just to make the whole variational principle working. In a sense, you want to avoid somehow the mixing between the bulk variation and the boundary variation, which is usually actually this problem is solved in such a way that by assuming some boundary conditions for the fields on the boundary and adding sometimes some counter terms to the action, you actually get the variation, you actually make this theory not to contain boundary variations. Another possibility is actually to add some fields, additional fields on the boundary, so as to cancel the boundary variations. Okay, so there are two ways of handling this problem. And in studying gravity, what you do, you know it probably in the case of asymptotically flat space-time, you really need to add some counter term to the action, which is proportional to the extrinsic curvature of the surface at large distance, right? Which is called Gibbons-Hawking-Yor term, or in the case of ADS, the situation asymptotically ADS system is by far more complicated. But it was solved at some point because ADS, asymptotically ADS spacetimes become pretty important, so people solved this problem. A remarkable thing about this BF is that actually, when you do the variation, it turns out that the boundary term, which has this form, at infinity, is actually vanishing, and it vanishes for two reasons. Well, first of all, because in this A4 part, the coefficient here, which has index A4 on shell, is proportional to torsion. Because torsion vanishes asymptotically, at least you don't allow the non-local fermionic sources, then this part vanishes, and another part vanishes because at the boundary, this BAB, the Lorentzian part, gives you the curvature, but the curvature must vanish asymptotically. Okay, so. And this can be traced to the pretty non-trivial, to the fact that there is this pretty non-trivial combination of topological invariants. And just because of this non-trivial combination of topological invariant, this boundary terms vanishes. One way or another, important thing about this formulation is that in the case with boundary, its natural takes care, at least for the of the asymptotic boundaries. And having solved this problem, you can actually think of something which is called Wald-Ayer charges. Wald-Ayer charges I will give you, so perhaps I skip something, just let me tell you what the idea is. Well, Wald and Ayer, or well, before Wald by himself, actually they find a very nice formulation in which they can define charges for generic gravitational theory. And one of these charges, which is pretty interesting, is entropy. Well, Wald also defines entropy, and he proves that indeed it's an entropy with a black hole horizon. So he takes his charge. The charge is an object which is associated with the boundary of space-time, and the boundary of space-time, in the case of black holes, there are two. There is a asymptotic boundary and the boundary at the horizon. So he calculates at the horizon, he actually calculates the charge associated. The charge is always associated with some time direction, right? We have conserved current, but conserved current, essentially from conserved current, by you actually construct a netted charge associating with some time direction, right? Okay? The netted charge is conserved, which means that its derivative over time is 0, so it's associated with some direction, with the time direction. All right? And, well, there is, of course, a complicated theory, pretty long and technical, but at the end of the day, the Wald proves that the charge associated with the time direction calculated at the horizon is actually proportional to entropy. So now, for those who know loop quantum gravity, the immediate idea is actually to calculate the entropy of black hole. And here is a surprise, because the entropy turns out to contain just the area term plus irrelevant constant contribution, this is the right expression for the black hole entropy in asymptotically ADS spacetime. What is remarkable about it, it does not contain any trace of inertia parameter, gamma. I started with a theory which contains inertia parameter, and according to loop quantum gravity calculation, the entropy of black hole should crucially depends on gamma. However, this calculation is telling you, which is purely classical calculation in a sense, is telling you that there is no way, that there is no point in which, the gamma disappear is completely, the calculation of entropy, the entropy is just given by the area with no relation to gamma at all. Which is kind of funny and interesting, because it actually is in a kind of considerable tension with the loop quantum gravity calculation. So this indicates and it supports claims of some people that actually the right calculation within loop quantum gravity somehow leads also to the calculation, to the result that entropy is not depending on inertia parameter, but then of course it's open to debate. I still have a minute. So what next? Well, there's several interesting things to investigate, and that's why I started thinking about it again. Well, I told you about this remarkable property of this theory, that it actually correctly handles, as it stands, it correctly handles the boundary terms. And that means that it's probably pretty well devised in order to handle these problems of gravity, of describing gravity in the kind of the local regions. Actually, you know that there is this problem of what is the local energy of gravity and stuff. And basically, if you have if you have local regions, essentially all the information about gravitating system are at the boundaries. In some sense, people may say that gravity is holographic, right? All the information, even for the local system, all the information is actually in the boundaries, not in the bulk. And there was a pretty interesting and beautiful paper by Donnelly and Friedel 3 years ago about describing the subsystems. They use it for gravity, but they use the metric formulation of gravity, which makes this theory pretty complicated. And I think that using this formulation that I already described you might simplify a lot this result that's been obtained here. There is some recent paper in which these people from Waterloo try to actually get to quantum gravity from some similar angle or related angle. They use a theory which they call BFCG theory, which is kind of a generalization of BF theory. Well, as just the letters tell you, this is BCFG, which is kind of two copies of BF theory in some sense. So it will be kind of interesting actually to investigate this thing. There seem to be, as I already told you, there seem to be a lot of mysteries remaining in the case of particle coupling, and the question if this topological, what is the topological limit, is a kind of the deformed effective theory of particles and fixed in this topological limit. What does mean this topological meaning physically, and so on. So there's at least three questions, or the big problems that actually I think still worth thinking about, and why that's the very reason why I thought it's worth actually describing the theory to you. And then at the end I will give you let me give you some guide to the bibliography. This is essentially the paper that all started, although Lee Smolin had this idea before, but this was when the variational principle for the theory were formulated first. Then it was investigated in more details in this paper when this idea about this perturbation theory in alpha started, although in some sense, I mean, the driving force behind it was Artyom Starodubtsev, that probably nobody remembers anymore except Tomasz. Here is the paper in which we discussed the coupling to the particles. We did investigated this gravity perturbation theory with Artyom. Here is when we, with Remik Durka, who was my PhD student at the time, we discussed the Hamiltonian analysis, and we discussed these netted charges and discovered that indeed the entropy does not contain the inertia parameter. And then, of course, there's some papers of Durka himself, and especially his very nice PhD thesis of, I think, 7 years ago, when he actually described all this in kind of a big details. And I think that's it. That's what I wanted to say. Thank you.
So any questions, comments, remarks? Feel free to ask.
Can I ask simple, primitive questions? So
Simple question. I'm always afraid of simple questions.
Well, so in this BM, you say that in this parameter it was alpha, yes.
Mm-hmm.
Goes to 0, you change the number of local degrees of freedom.
Mm-hmm. Mm-hmm. Yeah.
Why it is a problem? I mean, because you want to consider only local, but
no, the problem is that if you see, if you have the intuition about the perturbative expansion is that you start with some well-defined theory, which is the theory of your interest, and then you perturb the state a little bit, just probing how the theory responses, right, to the perturbations you introduce, right? And in this way you learn about the theory. However, here the problem is that this background is a completely different theory than the theory that appears to be in the case in which you introduce some perturbations. So you're not talking the same thing. So of course you can actually do the expansion, but it's not completely clear what this expansion actually means. Right? Because you don't expand about the same theory, but you expand about something completely different.
Are you aware about any other physical system, let's say condensed matter system, in which you have, let's say, topological state of matter, and then by introducing a certain perturbation, you produce a local degrees of freedom? By a certain symmetry gradient? Just to understand better the mechanism.
Well, you certainly can. Well, I never thought about it. It's a very good question. Certainly you can do it. I mean, for example, you can do it for 2+1 gravity. Certainly. You just break, I mean, you start with, you know, this Witten description of gravity and then break it down to the Lorentz symmetric. Can you do it? I'm not sure what is going to be the term that would do that, but probably you can do something like this. And we have a kind of a paper that does something like that, but it's just classical and not quantum mechanical. So, well, in principle, yes, but but it's a good question because I never saw any explicit model of this kind, but it's certainly possible to do, I believe.
Would be nice to see. And well, in Young-Mills case, you can do it, I guess. Similar, you can do it. You can actually try. For example, you can similarly formulate the Young-Mills theory, and then you certainly, I'm absolutely sure that you can add the term. So suppose you start with UN as Young-Mills, and then you certainly can construct a term that would actually break it down to some subgroup of UN. In the similar fashion as here. So this is possible. It would be interesting to see what this theory will be about. And can you do it for, let's say, electrodynamics, just to start with?
Well, electrodynamics, there is hard to break it down because it's just U1.
Yeah, but I mean, to generate a local gauge invariance, okay, starting from some topological theory.
I'm not sure. I mean, in this fashion, like here, probably yes. Probably yes. Well, I can see. Yeah, I think it's possible. I never tried, but I think it's possible.
And one simple question. The SO41, the CETER group was involved here. How crucial it is, I mean, for the construction?
It is crucial. It is. I mean, it's not crucial if it's SO41 or SO32, but it must be. Okay, so it's crucial because it should contain, at the end of the day, I want to be able to reproduce the gravity without cosmological constants. So this must be a group that actually contains Poincaré group in a kind of in a simple way. So it must contain the cosmological constant for this dimensional reason I told you. So I don't see any no-go theorem that you cannot do better than that. For example, you can try to do it as with a full conformal group if you like, SO42. I mean, the Stelle, I think the Stelle construction can be probably rephrased in this language too, but I never tried. Actually, it might be also another interesting project. It would be, you know, there was this, because this is based on the idea which goes down to McDowell-Mansouri paper, which was kind of famous in our times. You must remember that. There was at some point in 79 or 80s, it was one of the most famous constructions. Anyway, however, and then later, a couple of years later, Stelle and West actually generalized it somehow, taking as a starting point the full conformal group, if I remember correctly. And I believe that this can be generalized to this as well, but I never tried. There was this guy, Derek West, who was working with Baez, and I think he was doing something in this direction, but I'm not sure if he actually completed this research.
Derek Wise.
Derek Wise.
So question, I mean, is this something like general relativity or rather Einstein-Cartan version? Because, I mean, you have torsion, so... Well,
strictly speaking, it's Einstein-Cartan, but, you know, well, I mean, that's general relativity, right? So this is I would say, you know, I studied with Trautmann, so for me, Einstein-Cartan is the relativity.
Okay.
But of course it's not a metric formulation, but the you know, the tetrad formulation of gravity.
One of the transparencies is that there's some Lagrangian action, and you said that diffeomorphisms are mixed with this local stuff. How it comes about?
Oh no, I didn't say that. Sorry, so it must have been misunderstanding. Basically, if you start thinking about the symmetries of the theory, then you find out that there is one-to-one correspondence between diffeomorphism and local translation symmetry. So this is the, you know, for example, you can do it, of course, in the four-dimensional case, but this is most well known in the case. So it is described in details in this first paper of Witten on 2+1 gravity. So he shows that actually the local translation on shell, which is pretty important, so when the Ricci tensor is 0, there is the one-to-one relation between the local translations and diffeomorphism. So the local translation with some particular parameters are exactly diffeomorphism.
Any other question? If not, let's thank the speaker.
Thank you.